Hello and welcome to Module 10, Air Currents and what is also called Prevailing Winds. These are going to be your global wind patterns and how to happen. So we're going to talk about how air moves around up and down in the atmosphere. We're going to talk then about currents. And then we're, of course, going to talk about the fact that this is not a stationary planet. The planet is moving underneath. So you have this whole idea then of rotation and deflection, which is going to drive vertical air motion into vertical and horizontal. So kind of like a corkscrew. So hang on. Basic convection is just like you already know when material, especially some type of fluid, so a liquid or a gas, is going to be heated. Those molecules are going to get a lot of kinetic energy. They're going to get excited. They're going to move, and they're going to make that entire volume less dense. And because it is less dense than a surrounding area, it's going to rise. As you rise and get away from your heat source, you're going to cool. And as you cool, your molecules are not as invigorated anymore. They're going to start to pull together and become more dense. And as they become more dense relative to their environment around them, they're going to then fall back down based on their density or succumb to gravity. Atmospheric is a little bit different, though. It starts the same way because the sun drives everything in the atmosphere, and you must know that. The sun is the beginning for all energy that is going to be moving the atmosphere around, and that comes from that absorption idea, absorbing solar energy, especially your UV, because that's our most intense wave that we get here, electromagnetic wave that we get here, grabbing that energy, holding on to that energy, or pulling it into our mass. And then the leftover energy that we did not absorb is going to come back as that heat energy. But that is the driving force. So you have this thing, these weird words like adiabatic and latent and things like that. So you can pause here if you want to get those exact definitions down, up to you, but I do want to stick with this diagram more because this is a little bit counterintuitive. So I think everybody understands, okay, so the sun comes out and the ground in the bottom of the troposphere absorbs the solar energy, radiates back the heat energy. It's a whole concept behind the greenhouse effect. And then as that air begins to move up, we know that as you rise in altitude in the troposphere, it gets cooler and cooler and cooler. The air becomes less and less and less dense. So it almost seems like just as soon as that air would begin to rise because of its low density, it really should cool off and reaching the top of the troposphere. That's quite a distance to continue to be heated once you get less and less and less dense, and the volume just becomes so great and so low density up there that you would fall back down. So we have this thing called adiabatic cooling. And I will tell you, pressure wins with adiabatic cooling. With adiabatic cooling, the cooling effect of reduced pressure on the air rises higher in the atmosphere, and then it begins to expand. So yes, that parcel of air is becoming cooler. And that would mean that you would think that your particles then would start to come together again. But because you're moving up and away from gravity, you're actually becoming less dense because you're not as compressed. Your particles aren't as compressed. So you actually, as you rise, you do become cooler. Don't get that twisted, but you also become so less dense just because there's less pressure on you from gravity that you actually rise faster. And as you rise faster, you release what is called your latent heat. Now, I went to Miss Davis. The word latent means hidden or to disappear or not easily found. Latent heat is going to be heat that is present because you can't create or destroy energy. But that latent heat is going to eventually just spread out over that large volume as your volume of gas begins to, or your parcel of gas begins to expand, and you just distribute that little bit of leftover heat over such a large area that it doesn't disappear. Just collectively, it doesn't have any action on your molecules, on your gas molecules. Plus, you're condensing, so your water is now taking a lot of that heat with it, and that parcel of air is just going to continue to get less and less and less dense, and that is where you are going to have your adiabatic cooling. Once you hit the top of the troposphere, or you've basically cooled to the point where other factors are maybe tapping you down, you just ride across the top, and then the next parcel of air that's coming up behind you kind of like rail cars you forward, and then eventually now you've kind of hit your ceiling, and you're going to start to actually be pushed downward, because you're going to get caught in another convective current if you continue on, and you're really just going to get pulled back down. So there's all of these mini convection currents that are happening all over the surface of Earth, and it has a lot to do with topography. It has a lot to do with lateral movement of air or wind. And obviously water is going to have a lot to do with that, and the amount of sunlight, the duration of sunlight, where you are on the planet. There's just so many things, which is why meteorology is such a hard gig. People like to blame meteorologists. My brother is one, by the way. They never get it right. Well, you try tracking air on a planet that moves, and we have differentiated levels of heating that are going to occur as well. So, and it's changing. So as that air then begins to sink, it is going to warm up, because you are getting a little bit more compact. You're getting a little more compressed, so you are absorbing some of that solar energy as well. Plus, you're moving down in the troposphere, which we know gets warmer. But because you are moving closer and closer to gravity, you will actually accelerate, which is adiabatic heating, which again seems like you would pop back up again, but you don't. So that's adiabatics in a nutshell, because you are just dying to know. So again, you can go back and grab those definitions if you would like. Moving on to the Hadley cell. When you start talking about overall global wind patterns, we are going to start with the Hadley cell, because you...
Bye, Miss Taylor. Have a nice day.
You too, sweetie. Thanks. I'm on mute, so she's letting me go. Sorry. They were working on their stuff. So, you saw me jump. Pee my pants a little. Your Hadley cells, that was weird because I thought it was you guys. Oh, it's such a brain, whatever. So the Hadley cells are going to begin all of this, because you will notice that they are located on the equator. And the equator, I didn't mention this in the last video, the equator is always said to be the hottest section of Earth. It really isn't, because during the summertime, the northern hemisphere is going to be the warmest. And then during our wintertime, the southern hemisphere is actually the warmest. But twice a year, when you have your intermediate seasons, when you have your spring and your fall, the equator is actually going to be getting those nice direct 90-degree angle rays of sun. So twice a year, the equator is the warmest part on Earth. So that on average makes it the warmest place on Earth. So these Hadley cells are going to be where you have the hottest air that is going to be occurring, or the most effective heating that's going to be happening on Earth, right there along the equator. This is also what is called the ITCZ, which we'll talk about here in a second. So the Hadley is, you're going to see this quick rise of this very, very humid and a very quick rising hot air. As you reach towards the top, you are going to receive your adiabatic cooling and your adiabatic heating that's going to happen, which is why you have a whole lot of tropical storms that are going to originate around the equator. Obviously, one of the Hadley cells is going to rotate towards the northern hemisphere, and the other Hadley cell is going to rotate towards the southern hemisphere. But they divide right on that line, but you can start to see that mirror image from the top of the planet to the bottom of the planet, or northern hemisphere to southern hemisphere. And these steps are really, really good. I really like this particular diagram, because I think it does give you a lot of information on it. Okay, so your Hadley cells, where they're located, the intertropical convergence zone is just going to be the latitude that receives the most intense sunlight. It's going to be just north of the equator and just south of the equator, and these are where your two tropical zones are going to meet, your tropical northern and your tropical southern. Now, they do not mix, and we'll explain why in a second. That has everything to do with the Coriolis effect. So Your feral cells are really just kind of like a little sandwich product next to the polar cells. So you should have these definitions in the book. The polar cell is just going to be the cell that is located up at the poles. It is going to be one of the smaller cells. It is the least active, simply because it is not being driven as hard as the Hadley cell is going to be because of heat. So really, once you get your Hadley cells going, your feral cells are going to just kind of rotate air currents in a different direction, almost like if you think about spokes or gears, interconnected gears. So once the Hadley cell, which is clearly bigger and it's in charge because it's being driven by thermal energy, as it starts to rotate, it kind of pulls that band of air down with it and gives you that opposite effect for the feral cell. And then, of course, the polar cell is going to get in line with the movement of the gear and also continue to kind of wrap around. So your Hadley cell and your polar cell do move in the same orientation, either going, in this case, towards the North Pole, and then you would just mirror image that to then rotate everybody towards the Southern Pole because there's the Southern Hadley cell right there. So your feral cell, there is a definition for there, but it is just kind of the intermediate spoke. So your major cells, I'm now on this section of the notes where it's got the 3 for your major cells at the top. Your major cells are clearly going to be your Hadley, your feral, and your polar cell. Your intertropical convergence zone is basically where your 2 Hadley cells are going to meet along that equator. So for that diagram, you are going to see blue and red, blue indicating cooler parcels of air, red indicating warmer parcels of air, and that is going to be your high pressure and your low pressure. High pressure, this is all about being referenced to the ground. High pressure just means that... Oh, you know what? I'm going to pause there because I'm not sure I like that diagram. I'm going to pause. Okay. Yeah, let me pause there. Let me check something out. Okay. Plus, I'm over time. Guys need to tell me those things. I got scared. Forgot I was timing. Okay. We'll start here in just a second.